4 billion years ago, if you could stand on the surface of Mars and look north, you wouldn't see a desert. You wouldn't see rust-colored dunes or a thin, frozen sky. You would see an ocean, waves crashing against dark volcanic shorelines, water stretching to the horizon under a thick, warm atmosphere, rivers carving deep channels through mountain ranges taller than anything on Earth, rain falling on a world that looked more like our planet than the dead rock we see today. Mars was not always red. Mars was not always dead. There was a time, a long time, when Mars was blue, and we now have the evidence to prove it. In February 2025, China's Zhurong rover detected something buried beneath the Martian surface that scientists had been searching for decades. Ancient beach deposits, layers of sand tilted at the exact angles you'd expect from millions of years of wave action, buried 30 to 100 feet underground. The fossilized remains of a coastline. Not theoretical, not inferred, detected, measured, published in the Proceedings of the National Academy of Sciences. Mars once had an ocean so large, it covered nearly half the planet's northern hemisphere. And what happened to that ocean is one of the most dramatic, most tragic stories in the entire solar system. If you're the kind of person who looks at the night sky and wonders what we're missing, you're in the right place. This is Final Frontier Space. Hit that subscribe button right now. Tap the bell so you never miss a deep dive. And drop a like on this video. It genuinely helps us reach more people who love the cosmos as much as you do. Today, we're going back in time, 4 billion years, to the Mars nobody knows. Chapter 1. The Blue Planet Next Door. To understand what Mars once was, you first need to understand what Mars is. Today, Mars is a frozen desert. Its atmosphere is less than 1% the density of Earth's. Surface temperatures average minus 63 degrees Celsius. The air is 95% carbon dioxide. There is no liquid water on the surface. There is no magnetic field protecting the planet from the sun's radiation. Mars is half the diameter of Earth. It has about 10% of Earth's mass. Its gravity is only 37% of ours, meaning you could jump nearly 3 times higher there. And despite being smaller, Mars has roughly the same amount of land area as Earth, because 2/3 of Earth's surface is covered by oceans. Ironic, isn't it? The planet that lost all its water has the same land area as the planet that's covered in it. But Mars is also home to the most extreme geology in the solar system. Olympus Mons, the tallest volcano in the solar system. 22 kilometers high, nearly 3 times the height of Everest. Its base is so wide it would cover most of France. If you stood on its summit, you wouldn't even know you were on a mountain, because the slope is so gradual that the curvature of the planet hides the edges from view. Valles Marineris, a canyon system stretching over 4,000 kilometers across the Martian equator. 10 times longer than the Grand Canyon, 7 times deeper. If it existed on Earth, it would stretch from New York to Los Angeles. Hellas Planitia, an impact basin over 2,000 kilometers wide and 7 kilometers deep. Created by an asteroid impact so violent it would have vaporized oceans and reshaped the entire planet. These features tell a story of a world that was once violently, powerfully alive, volcanoes erupting for hundreds of millions of years, asteroids reshaping continents, and water, vast amounts of water, flowing across every surface. But 4 billion years ago, something began to go terribly wrong, and it started deep inside the planet. Chapter 2. When Mars was alive. Rewind to 4 billion years ago. The era geologists call the Noachian. Mars during this period was an entirely different world. The atmosphere was thick. Dense carbon dioxide and water vapor created a powerful greenhouse effect, trapping heat and warming the surface to temperatures where liquid water could exist. In 2025, NASA's Curiosity rover found cedarite, an iron carbonate mineral, in rock samples from Jezero Crater, direct chemical evidence that Mars once had a dense, warm CO2 atmosphere. Under that thick sky, water flowed. Not just a little, everywhere. Valley networks, thousands of them, carved into the ancient highlands of Mars. These aren't flash flood channels. They're branching river systems, with tributaries and drainage basins that match the patterns we see on Earth. They required sustained rainfall over millions of years to form. And in December 2025, Perseverance found something remarkable in Jezero Crater. White kaolinite clay scattered across the crater floor. On Earth, kaolinite only forms after millions of years of warm, rainy conditions, tropical, humid climates, the kind of weather you'd find in a rainforest. Let that sink in. Mars may once have had a climate similar to a tropical rainforest. In the northern lowlands, a vast ocean formed. Scientists call it Oceanus Borealis, the Northern Ocean. At its peak, it may have covered nearly a third of the planet's surface. The water depth in some areas could have reached over a kilometer. Rivers fed this ocean from the highlands. Deltas formed where those rivers met the sea, exactly like the Nile Delta or the Mississippi Delta on Earth. Jezero Crater, where Perseverance is exploring right now, was once a lake fed by rivers, with a clearly visible fan-shaped delta still preserved after 3.5 billion years. Volcanic activity was intense. The Tharsis volcanic region, home to Olympus Mons and 3 other massive shield volcanoes, was erupting continuously. These eruptions pumped greenhouse gases into the atmosphere, keeping Mars warm. Hydrothermal systems, places where hot volcanic water mixes with minerals, created environments that on Earth are teeming with life. Deep beneath the surface, Mars had something else. Something critical, a magnetic field. Like Earth, early Mars had a liquid iron core that generated a global magnetic field. This invisible shield deflected the solar wind, those streams of charged particles constantly blasting out from the sun. Without it, the sun would strip away the atmosphere molecule by molecule. Time equals 600 milliseconds, slashed for hundreds of millions of years, this shield held. Mars was warm. Mars was wet. Mars was protected. And then, the shield fell. Chapter 3. The Death of a World. Here's what killed Mars. It wasn't an asteroid. It wasn't a cosmic catastrophe. It was something far more subtle and far more inevitable. Mars is small. That's the fundamental problem. With only 10% of Earth's mass, Mars's interior cooled far faster than Earth's. And when the interior cooled, the liquid iron core began to solidify. On Earth, our outer core is still liquid. It churns and flows, driven by heat from radioactive decay deep within the planet. This churning liquid metal generates Earth's magnetic field through a process called the dynamo effect. It's the reason we have a magnetic field. It's the reason we have an atmosphere. It's the reason we're alive. On Mars, the dynamo stopped. Research published in recent years pinpoints the moment. Approximately 4.1 billion years ago, Mars's magnetic field collapsed. Not gradually over billions of years, rapidly. In less than 20 million years, the global magnetic shield that had protected Mars for hundreds of millions of years simply vanished. And what happened next was catastrophic. Time equals 600 milliseconds greater than without the magnetic field. Mars was naked. The solar wind, a constant stream of charged particles traveling at 400 kilometers per second, began to slam directly into the upper atmosphere. NASA's MAVEN spacecraft has been studying this process since 2014, and in 2025, MAVEN made a historic first: the direct detection of atmospheric sputtering on Mars. Sputtering is exactly what it sounds like. High-energy particles from the solar wind collide with atmospheric molecules and literally knock them into space, one by one, molecule by molecule, over billions of years. MAVEN analyzed 9 years of orbital data and found that lighter atmospheric particles were being stripped away at high altitudes, while heavier ones remained lower. During solar storms, the rate of loss intensified dramatically. And early in Mars's history, when the young sun was far more active and produced far more ultraviolet radiation, the stripping would have been orders of magnitude worse. The atmosphere thinned. As it thinned, the greenhouse effect weakened. Temperatures dropped. The oceans began to freeze. Some of the water evaporated into the thinning atmosphere and was itself stripped away by the solar wind, molecule by molecule, into the void of space. Some of the water sank underground, freezing into massive reservoirs of subsurface ice, and some, an unknown amount, was locked into hydrated minerals in the rock itself. Mars didn't lose its water in a single event. It lost it slowly. Over hundreds of millions of years, a planet bleeding into space. Imagine watching a world die in slow motion, the ocean retreating year by year, the shoreline pulling back, exposing dark volcanic rock that had been underwater for millions of years, the rivers running thinner, the rain stopping, the sky thinning from blue to pale pink to the thin, rust-colored haze we see today. By 3.5 billion years ago, the great ocean was gone. The rivers had dried, the volcanoes were slowing, and Mars began its long, cold descent into the frozen desert it is today. Chapter 4. The Evidence We Found. For decades, scientists debated whether Mars truly had an ocean. The evidence was suggestive but indirect. Orbital images showed features that looked like ancient shorelines, but they weren't at a consistent elevation, which you'd expect from a real coastline. Then the rovers arrived, and the evidence became overwhelming. Curiosity, exploring Jezero Crater since 2012, found rounded pebbles in ancient riverbeds. Pebbles that had been tumbled and smoothed by flowing water, the same way river rocks are rounded on Earth. The size and shape of these pebbles told scientists the water was about knee-deep and flowing at roughly a meter per second. A pleasant stream. Curiosity also found layers of sedimentary rock, clay minerals called smectites, that only form in the presence of liquid water over long periods, and the siderite discovery in 2025 provided the smoking gun for a dense, warm atmosphere. Perseverance went even further. Jezero Crater was chosen specifically because orbital images revealed a beautifully preserved river delta, a fan-shaped deposit of sediment where an ancient river once emptied into a lake. In 2024 and 2025, Perseverance confirmed that this delta is exactly what it appears to be, a real ancient river delta with layers of sediment deposited by flowing water over millions of years. And then came the organic molecules. Perseverance detected polycyclic aromatic hydrocarbons, complex organic molecules preserved in sulfate minerals on the crater floor. These are not proof of life. Organic molecules can form through non-biological chemistry, but they are exactly the kind of molecules you would look for if you were searching for evidence of ancient microbial life. In September 2025, researchers published a landmark study identifying 24 distinct mineral types in Jezero Crater, revealing 3 separate stages of water activity. The water chemistry shifted over time, from harsh, acidic conditions to more neutral, potentially life-friendly environments. Think about what that means. Mars didn't just have water. Mars had water with the right chemistry, at the right temperature, for long enough periods that life as we know it could have emerged. And then there's the Zhurong discovery. In February 2025, China's Zhurong rover, exploring Utopia Planitia in Mars's northern lowlands, used ground-penetrating radar to look beneath the surface. What it found were thick layers of sand-like material, tilted at 6 to 20-degree angles, buried 30 to 100 feet underground. These layers stretched nearly a mile along the rover's path. The tilt angles matched the slope of beach deposits on Earth. The layering pattern matches coastal sediments formed by sustained wave action. The depth is consistent with burial over billions of years of geological activity. These are the remains of a beach, an ancient Martian beach, buried beneath the dust of 4 billion years. Chapter 5. The Water That Never Left. Here's something most people don't know. Mars didn't lose all its water. In August 2024, scientists analyzing data from NASA's InSight lander made a staggering discovery. Using seismic waves from Marsquakes to map the planet's interior, they found a massive reservoir of liquid water trapped deep underground. Not ice, liquid water. The water sits 11 to 20 kilometers beneath the surface, trapped within fractured igneous rock. At those depths, the crust is warm enough for water to remain liquid, and the amount is extraordinary. If you could bring all of that underground water to the surface, it would cover the entire planet to a depth of 1 to 2 kilometers. That's roughly the same volume as the ancient ocean that existed 3 billion years ago. The ocean didn't disappear. It sank. Over billions of years, as the surface froze and the atmosphere thinned, water migrated downward through cracks in the Martian crust. It seeped through porous volcanic rock. It filled fractures and voids deep underground. And there it stayed, insulated by kilometers of rock and warmed by the residual heat of Mars's still cooling interior. A 2025 study published in the National Science Review refined these findings further. A low-velocity seismic zone between 5 and 8 kilometers depth contains water-saturated, high-porosity rock. This zone alone holds an estimated 500 to nearly 800 meters of water if spread globally. Mars is not a dead, dry world. It's a world with an ocean hidden beneath its skin. And this changes everything about how we think about life on Mars. If life ever emerged on ancient Mars, during those warm, wet hundreds of millions of years, it would have had one strategy for survival as the surface froze. Go underground. Follow the water downward, into the dark, into the warmth, into the deep rock where liquid water still flows. On Earth, we know this is possible. Deep beneath our own surface, in mines 2 kilometers down, in aquifers buried under ancient rock, we find thriving ecosystems of chemotrophic bacteria, organisms that live on chemical energy from rock and water, completely independent of sunlight. They've been down there for millions, possibly billions of years. If Mars ever had life, it may still be there, right now, deep underground, in water that has been flowing in darkness for 4 billion years. Chapter 6. What Mars Teaches Us About Earth. The story of Mars is not just a story about another planet. It's a warning. Mars shows us what happens when a planet loses its magnetic shield, when the atmosphere thins, when the greenhouse effect collapses. when the water disappears. Earth and Mars started in remarkably similar conditions. Both formed from the same solar nebula 4.5 billion years ago. Both had liquid water. Both had thick atmospheres. Both had volcanic activity pumping gases into their skies. Both had magnetic fields. The difference? Size. Earth is large enough to keep its interior hot for billions of years. Our core still churns. Our magnetic field still holds. Our atmosphere stays. Mars was too small. It cooled too fast. And it paid the ultimate price. When you look at Mars through a telescope, you're looking at what Earth could have become. A planet that had everything it needed for life and lost it all. Not through some sudden catastrophe, but through the slow, inexorable cooling of its own heart. Our magnetic field is the only thing standing between us and the same fate. A thin, invisible bubble of magnetism generated by liquid iron churning 2,900 kilometers beneath our feet. Without it, Earth's atmosphere would be stripped away over millions of years. The oceans would evaporate, the surface would freeze, and our planet would become another Mars. Mars is not just a neighbor. Mars is a mirror, and what it reflects back at us is both humbling and terrifying. But it's also inspiring, because we figured this out. We sent robots to another planet. We drove them across ancient ocean floors. We analyzed rocks that were last touched by water 3 billion years ago. We used seismic waves from Marsquakes to discover an ocean hidden 11 kilometers underground. We detected the fossilized remains of beaches buried beneath 4 billion years of dust. From a small rocky planet orbiting an ordinary star, we reached out across 55 million kilometers of empty space and read the geological autobiography of another world. We are a species that finds oceans on planets where no ocean has existed for 3 billion years. We listen for life in places no human has ever been. We reconstruct entire worlds from the chemistry of individual rocks. That is not just science. That is the most extraordinary thing our species has ever done. 4 billion years ago, Mars was blue. It had oceans, it had rivers, it may have had rain, it may have had life. Today, it's a frozen desert with a thin pink sky and dust storms that can engulf the entire planet. But beneath that dust, beneath that frozen surface, buried in the ancient rock, the evidence is still there. Beach deposits, river deltas, clay minerals, organic molecules, and an ocean of water, still liquid, still waiting, 11 kilometers underground. Mars lost its oceans, but it never lost its secrets, and we're only just beginning to uncover them. If this video changed the way you think about Mars, do me a favor. Hit that like button. Share this with someone who loves the cosmos. And if you haven't already, subscribe to Final Frontier Space and ring that notification bell. We go deep into the places nobody shows you, and we do it every single week. I'll see you in the next one. Stamai.